Hi there. In this demo, we're going to show how Apromore can move a team from we think we know what's happening to we can prove it with data and estimate and compare return on investment before we change anything. Today's dataset is a telecommunications support ticketing process, captured as an event log over roughly 1 month. We'll work with 3 key role groups: support agents, who handle ticket categorization and customer queries; supervisors, who handle escalations; and field technicians, responsible for on-site resolution. The investigation has 2 goals. First, reduce case duration to promote faster ticket resolution. And second, reduce processing costs for more efficient execution and resourcing. The frame is perception versus reality, what the happy path or ideal process looks like on paper versus what the data says actually happens on the ground in the real world, including case variants, exceptions, delays, and rework like reopened tickets. To start, we load the event log in Apromore and discover the real process before modeling. Let's start by mining the process map. Even without touching simulation yet, Apromore's discovered process map is already telling us where the work really flows, where it waits, and where it loops. Now we overlay average case duration on the process map. In Apromore, the dark and thick paths are the ones to pay attention to. Those are the frequent or slow transitions that dominate the overall experience. Immediately, we can see in this ticketing process that there is a slow processing time for technician assignment and dispatch, pointing to delays in technician self-assignment. Escalations to supervisors also introduce long waiting times, becoming a clear bottleneck. Let's look at this from the role perspective as well. So we already have 2 strong hypotheses. First, technician dispatch could be delayed because technicians self-assign cases, and that doesn't happen quickly enough. In practice, they must access a system and assign cases to themselves manually. This can be automated. Second, supervisor escalations are delayed because supervisor capacity is constrained. This requires a different solution, either hiring additional staff or rearranging task priorities. Let's also bring money into the picture and add cost overlays. Now we flip to the average cost overlay. This is where the story stops being process curiosity and becomes management obvious. The analysis, using role-based hourly cost models, indicates that technician assignment and escalation to supervisor are high-cost areas. And if those steps are also slow, then we're not only wasting time, we're paying for the waiting. At this point, before we simulate anything, we can already make a defensible deduction. The biggest return on investment opportunities will be interventions that reduce waiting in the technician dispatch step and the supervisor escalation step, because those delays are both time-heavy and cost-heavy. We start by calibrating an as-is simulation for the process baseline first. This reconstructs the digital process twin. A critical discipline step. We don't jump straight to simulated improvements here. We first reconstruct and calibrate an as-is simulation model so that when we compare scenarios, we compare process design changes, not accidental optimizing against real-world noise like absences or seasonal effects. We explicitly frame simulation as a way to do structured comparisons between as-is and distinct to-be scenarios. This is also where role-based hourly costs matter, because it lets us quantify time saved into money saved across roles. First, we pursue Objective 1, reduce case duration. The intervention here is to automate technician assignment. In the current process, technicians assign themselves, which introduces delays. The proposed fix is a bot that assigns technicians automatically within 10 minutes based on ticket type and availability. Expected impact: reduced waiting and faster resolution. When we run the simulation, the to-be map shows a clear improvement. This intervention produces about a 30% faster ticket resolution in the simulated results. Now, we want to see how this compares to other potential interventions, so let's investigate a different setup. Intervention B: add an extra supervisor. The second intervention is a classic approach. Add a supervisor to reduce escalation delays. The expected impact includes shorter waits for escalated cases, but it also adds costs that we should quantify. In the simulation results, this approach improves overall case duration by about 44%. That's actually better than the bot automation on time alone. Let's compare outcomes side by side, considering both duration and cost impacts. Here we show the case duration frequency comparison. You can see the distribution of case duration buckets shift toward lower values. The simulated to-be scenarios show fewer long-running cases. Now the punchline. The extra supervisor helps with time, but it doesn't win on return on investment because of the associated costs. The simulations report average cost per case roughly as follows. Baseline as-is scenario, 1,563 Rand. Automated technician assignment simulation, 1,067 Rand. Extra supervisor simulation, 1,511 Rand. So we can make a decisive managerial conclusion. If the primary KPI is speed, extra supervision can be effective. If the KPI is comparative return on investment across both time and money, the technician assignment automation is the better choice. That line of investigation looks at case duration as the primary KPI. But what if we place more emphasis on the cost side? Let's look at Objective 2, reduce costs. Now that we've already seen technician assignment automation creates cost savings, the digital process twin can be used to test an additional cost-focused intervention. This time, automating agent assignment instead of relying on self-assignment or rules-based assignment. Under this objective, Intervention A automates technician assignment. As in the previous benchmark, this reduces average handling cost per case by about 31%. Now let's move to Intervention B, automate agent assignment. To simulate this scenario, we create a bot role, assign it the task, then remove the existing role. We then modify the discovered parameter for the assigned to agent task, assuming that an RPA solution brings this task's processing time down to about 10 minutes, following an exponential distribution. The agent assignment bot shows a smaller cost saving, around 6%. Let's look at resource utilization, which matters for decision making. The chart shows that agent and technician time is freed up under automation. So the best decision is to automate the step that is both high weight and high cost, and is frequently performed. In this case, that's technician assignment. At this point, the investigation can extend to further solutions with the goal of picking the best comparative return on investment. For now, let's conclude the demo findings. The investigation's conclusion is straightforward. Technician assignment automation proves out as the best balance of efficiency and cost. Adding a supervisor can improve speed, but falls short as a cost-cutting measure. Agent assignment automation shows limited gains, so the process improvement recommendation is as follows. Implement automation for technician assignment as the highest return on investment intervention in this telecommunications support process. What else does Apromore enable beyond investigation? Continuous monitoring and stress testing. Once the change is implemented, the digital process twin isn't done. It becomes an operating capability. We can use the digital process twin in Apromore to monitor KPs and bottlenecks continuously, stress test caseloads during busy seasons, evaluate policy or system changes before rollout, and support dynamic workload balancing and ongoing reporting. And that's the core value. Apromore lets you diagnose with evidence, test interventions safely, and choose the best path to maximize return on investment before spending money or disrupting operations.